Hello, this is the recorded lecture for HSC 400 Healthcare Analytics, and we'll be looking at Chapter 9 in this particular lecture, which are really an overview of our basic statistical methodologies that we use in analytical approaches. And we'll look at the control chart principles, some pros and cons to using certain charts, and whether they're applicable and whether they're not applicable. Now, there are complementary methods to measure the impact of change or innovation. We can have lots of ways to show that. For statisticians, that's looking at some specific calculations. But for the rest of the world, you have to be able to take that information and sort of create visualizations for them so they can see that. And we do that with lots of different kinds of charts and sort of diagrams. Now, statistically, we do that. We use statistics and we use control charts. And our statistical methods help determine the changes in performance. Well, they rely on those statistical tests to determine if the changes in quality or performance or other metrics are statistically significant. And sometimes that's a really difficult little nugget to get a hold of, because sometimes we put in a change and we get some sort of slight benefit from that. Maybe it rises 2%. We think we've created this wonderful change, when maybe it's just a simple variation in the process and what we did didn't do a darn thing. So understanding how that applies is kind of important. And then the truth is, the graphical approaches that we have, that we'll talk about these different charts of statistical process control charts. We'll see those as we go through, and that help us to really look at that information, and then through some calculation determine whether what we've done is really significant or not. It's interesting that when I was doing my dissertation and I did my study, some of the things I thought were going to be distinctively different, just looking at the data, turned out to be not very different. That they fell within the same realm as if nothing happened. And then I had other areas which I thought weren't really significant. Turns out they had major statistical differences when we ran the methodologies on them. So sometimes it's not just really eyeballing that really helps, and it is contrary to eyeballing. Now, we have statistical methods for detecting changes in quality and performance, and as analytic professionals, we should make statistics really more understood. You can't really turn everybody into a statistician, but you have to have a informed user, if you will, or an informed audience. And so the problem that happens sometimes is statisticians get into techie talk, is the word I use, and they begin by sort of loading you down with all this information that you don't use or haven't used since you were in college, or never used if you weren't in college, and then you get lost in the methodologies. It's supposed to be impressive, but it's really more of creates confusion. So most QI methodologies don't require really extensive statistical knowledge or use of a sophisticated, can't say that, statistical methodology. They really don't need that. They tend to use something a little more simpler. Now, statistical analysis is necessary to evaluate performance when the quality of the data being used is poor. It allows you to pull out some information. I have a term that I used to use when I was in the military, and it's called dirty data. We can look at dirty data. And the interesting thing about dirty data is this: is that if you have clean data, and then you compare it to dirty data, you can't do that, because the two are so different. And one has all sorts of errors and bizarre things in it, one doesn't. On the other hand, if you have two groups of data, and they come from the same source, and the level of dirtiness, I'll try to say it that way. This makes my statistician crazy when I say this. If the level of dirtiness is the same errors occur in both, then you can compare one to the other and get some information out of that. Is it absolutely perfect information? No, but it might give you enough to make some decisions. If the wrong indicators were developed in the quality improvement project or process improvement project early, then that's a problem. And if there's no change or little change in performance, then statistical analysis is really helpful. And like I said, what you may see as no change may really be significant change as far as statistically speaking. Now, statistical application, I got to get this down, I can't believe I say this all the time, can be applied in two ways. We use what are called descriptive statistics or inferential statistics. And descriptive statistics are used to describe a large number of values for observation, and that's when we're taking a sample to represent a whole entire population. We take a random sample from a population, and we then make decisions on the population based on this random sample, assuming that the sample is homogeneous with the rest of the population. That isn't always true, but it mostly is true. And so it's based on that faith that that's what's going to happen. Now, like I said, it represents the entire population based on a sample size, and it's commonly used, and some of the things we look for are mean and median, which we've talked about before. Well, that's some of the ways we're looking at to see where the commonality is. Now, inferential statistics, we analyze a sample of data to help draw conclusions about a population, and this helps us to evaluate central tendencies also. So it can be descriptive or inferential, and they're quite different in how we approach them. One of the methods we use, whether we look at the difference in values before and after a change has been instituted, is known as what's called hypothesis testing. Now, what basically a hypothesis says is something is or isn't going to happen, and you're saying it's not going to happen, and if it proves wrong, then it's going to happen. If it proves wrong, then if you say it's not going to happen, and you prove you're wrong, then it's going to happen. And the strange thing about hypothesis is that you generally go in saying that nothing's going to happen. Your hypothesis is there'll be no change between these two samples, even though you're kind of hoping there is. And so you have to prove the hypothesis wrong by saying, okay, there is a change. And we'll show you how to do that. And that involves a test of statistical significance. It helps determine whether differences between two groups are due to actual differences or serendipity. And serendipity just means pure chance. So, in other words, you might think there's a difference, but the way I look at this, so I used to I had clinics that I used to manage, and the senior leadership at that time would look at our clinics as far as the revenue we created and the expenses we created month to month, and they make decisions literally month to month for improvement of those clinics. And I got kind of tired of that because medicine has seasonal variation just like everything else. So I went back and looked at the seasonal variation for the clinics over the last 5 years and developed a baseline from month to month to say, okay, the baseline for this month consistently is in this area. And then I would compare our revenue and expenses to that month. And because some months you buy supplies. There's certain months you buy supplies every 2 months, and every 2 months your expenses are higher, and it won't match your revenues. And every other month from that, your revenues are high and your expenses are low. So people make all these decisions, and they think that what they were doing was really helping when it really wasn't. And I presented that to senior leadership and said, okay, here's the seasonal variation of 5 clinics. Here's the 5 clinics apart. Here they are together. Notice how they have the same commonalities as far as what happens from month to month, seasonal variation. It's not the same in January as it is in July, for instance. And I said, so you can't really make decisions about whether a clinic is doing well or not doing well based on looking at a 1-month snapshot. You really have to look at it compared to its seasonal variation. And they finally got it, but boy, it was a hard road because they just wanted to make all these decisions from month to month. And so people were like jamming and cramming back and forth to try to make it happen. So it's important that when you go to this process, you really affect a change. So hypothesis testing is really that. Now, here's a good, we look at this, the hospital stay, for instance. We have the before and after an implementation of the new discharge protocol. So we said that, okay, length of stay before the discharge protocols was 4.5, and then after was 3.7. And so if we took this measurement, in January, and we took this measurement in August, is this really a change, or does this just represent seasonal variation? So that's kind of an important point. So let's look at this. Hypothesis usually starts, as I said, with a negative assumption, i.e. there's no difference between the two groups. And we call that the null hypothesis. Null is actually another term for zero, or negative, or not, if you will. If the null hypothesis proves wrong, then there is a difference between the two groups, most likely caused by the change instituted. Now, I know this sounds really crazy to do that. Why would you go and say, I think there's a change? And the problem is that it's just it's the language of statistics that sort of directs this. If you learn a foreign language, German, for instance, the verb goes before the subject, where in English the verb is after the subject. So consider this like learning another language, and that is that the hypothesis is always negative. We think this is not going to happen, even though in your heart of hearts you're hoping and knowing it's going to it did happen. You still have to go with that negative assumption. So when you start to compare the performance between two groups, there's a common statistical test to evaluate, like in the pre and post evaluation of intervention, and that's called a t-test. And the t-test is a statistical method that can be used to help determine if the statistical parameter, that's the mean or the average, is the same when compared between the two groups. So what you do is you look for the means of each group or the average of each group, and you run tests on them. You run this t-test on them, and the t-test will help you to determine whether it's really a change. You don't just look at the total numbers, you look at the average. And so the t-test can be used in two situations. If you have what's called a one-sample t-test, it's used to compare one point of interest to the sample. So in other words, the one sample is really, we're looking at that single sample. But a two-sample t-test is used to compare the performance of two groups, one group to the other. So the t-test can be a single sample or a one-sample t-test or a two-sample t-test. And all it does is looks at the mean, the average, if you will, of between two groups and makes some assumptions based on that. Now, the t-test can be applied to pre- and post-change groups to determine if there's a statistical significance between the two. And normally statistical tests such as the t-test would be performed in a statistical software package or a spreadsheet with statistical capabilities. Now, it's really interesting because there are some very intricate, very elaborate, very sophisticated statistical software packages, but you could do many of the statistical analyses in a simple Excel spreadsheet, because it's become, the spreadsheets become more and more like a database of statistical software, and the databases have become more and more like spreadsheets. They've kind of crossed over in some ways, and a lot of people think we should just have one, instead of having a spreadsheet in a database, we should have a database spreadsheet. And there are some softwares that sort of follow that. Now, comparing performance between two groups, you have to understand the statistical report. You get this kind of gobbledygook out of here, and you see all these numbers. There's t equals this. There's a p-value, which we'll talk about in a bit. And then we look at differences. We'll look at p-value, which is going to be important. We'll look at the confidence intervals between what two levels, if you will. And we'll talk about the means of the differences. So we'll talk about all of this in just a minute in the following slides. But this is what you get out in many of the software packages. Not helpful to the non-statistician. So what do the results mean? Well, if we compare the pre and post tests and the difference was 0.92 days, the chance to our confidence in the results would improve, with two repeated tests demonstrating the same trend. If we repeated the pre and post tests 100 times, let's say, and found that 95 out of 100 produced similar results, our confidence would be pretty high that there was a significant change. Obviously, 95 out of 100 is good. On the other hand, if we were more like 60 to 100, we'd be less confident, because it kind of starts to approach, like, you know, the law of averages, 50-50. So finally, if the similarity was 50 or less, we would be deemed that there was no statistical differences in the two, what we did if we provided a change. Now, statistical analysis such as the t-test provides what's called a quantitative assessment of this confidence that we just talked about, and that's in the p-value. Okay? The common p-value target often used in scientific research is something less than 5%. The p is less than 0.05, which means that there would be less than 5% chance of obtaining the observed results if the null hypothesis was true. When you want things to go your way, you're hoping to see this, because it says that the chances of it not working is less than 5%. So in other words, think about this as a negative. So the null hypothesis says we don't think it's going to happen, even though in your heart of hearts you want it to happen. And so if this p-value says, well, this is not going to happen, if it's less than 0.5%, then the chances of the null value are kind of like not very good. So if we look at our p-value from the gobbledygook we had in the slides before, in the date given 2 slides previously, the p-value was estimated at 2.2 to the -16th. Now you have to understand that, to the -16th. That is way less than 0.05. So that suggests there's an extremely small chance of any change. There's no statistical difference between the groups. So even though we saw 0.92 days difference, really wasn't statistically significant. So when you look at this, you say to yourself, whoa, there's a big change. And you get to this, and you say, wow, not much of a change. And so what you sometimes see intuitively is not what is there actually. So this 2.2, and by the way, that when you go to scientific notation, the E means that you take it out 16 places, if you will. So you have to take it out -16 places. So this is 0, this decimal point will go way out here. So it's like 0.00016 of those to 2.2. So it's 0.0016 times 16 to 2.2. So it's way, way out there. Very, very, very small. Now, when you compare performance between two groups, we can sometimes use what's called the confidence interval, and that's when we compute large range of numbers between which means the true value is expected to lie. In our example, we had that range of minus 1.039 to minus 0.922. In other words, we could say that there's only a 1 to 20 chance that the true difference between the groups is not within the range. So what it basically says is that it's not very large. So if the confidence interval is included as 0 between 0.5 and minus 0.5 and minus 0.5, it would suggest no difference. So this is close enough that it's not much, if you will. And so you see the confidence interval is not much. Now, when you compare performance of more than two groups, let's say if an analyst needs to compare the results from 3 different data sources. I used to compare my clinics from clinic to clinic to see what the differences were in the clinics, and I would run these multiple analyses to see what was going on. And I'd compare the results of the length of stay, or not the length of stay, but I'd compare the results of what the clinic production was between those 3 areas. In this case, we look at 3 hospitals and their length of stay for patients who have undergone a coronary artery bypass graft or a CABG. Now, the statistical test for this situation is called the analysis of variance, or ANOVA. And it compares the variance between the groups and compares the ratio of within group and between group variance. That sounds like a lot of gobbledygook too, unless you're a statistician. So let me see how I can do this. So let's look at this. We look at the bypass grafts patients and their lengths of stay. So if we look at just the lengths of stay between the 3 groups, we can say, okay, these 3 groups have a different length of stay, and we can look at the differences between Hospital 1 and Hospital 2, Hospital 1 and Hospital 3, and Hospital 2 and Hospital 3. We can look at those differences between them, and we can see if there's any commonality between them, and that's what ANOVA does for you. It really helps you decide whether what you're doing really makes a change. Let's say we did an intervention in these 3 hospitals, and only 1 hospital had any change whatsoever, and that change was was not even statistically significant. That was at point, 0.000.16 places, 2.2, pretty small. So it wasn't really much of a change. But the other 2 hospitals, the confidence interval was something different. So we would see that there was something different at that one hospital compared to the other 2 hospitals. And so you see that there was a difference, and maybe there was something going on that was an aberration, something that wasn't really normal thinking from that hospital to the other 2 hospitals. So it also, if the variation between the groups is much higher than the variation within the groups, and the F statistic exceeds critical value, and F statistic says, okay, if this is too high, that means there's a difference between the groups that can be considered statistically significant. So that F statistic is another way to look at the information. Now, we look at sample hospitals, like the stay for CABGs. We can see here we have the hospital A, B, and C. Here it's 8.5 days, 9.8, 8.9. So you say, well, hospital 8.5 is doing great. Hospital 9.8 is not doing so great. 8.9 is in the middle. Until there's other things you have to think about. If you look at the criticality of patients, for instance, maybe hospital A only takes does multiple CABGs. So they don't do a single coronary artery bypass graft on a patient. They only do them when there's 4 or 5. They're the most difficult patients. So their length of stay may or may not be higher based on that. So the people with 9.8, they have a higher length of stay because the person's in surgery longer, and that statistically may make them have a longer length of stay. Where the people in hospital A, maybe they only do a hospital CABG on patients that have they need a single bypass, so their length of stay is different. So this number doesn't mean anything until you start applying those kind of priorities. Now, the different scenarios for which you might consider using the different types of ANOVA tests is that you have a one-way between groups. Use that when the performance of 3 or more groups needs to be compared, and that's what we just talked about. One-way represented measures you use when the performance has been measured a few times per project, mid-project, post-project, and you test for a statistically significant change in performance. This tells you, the ANOVA test tells you, did I create a change? So we started the project, there's the pre-project, it should be mid-project and post-project, and it didn't create this change, not per project, pre-project. And the answer is, if there's no difference between these three statistically, you created no change, even though you may have a more positive number here. Now, a two-way between groups used when looking for more complex interactions, more than one variable. And this is like, for instance, we look between 3 hospitals and we start comparing which one has the higher severity in their patients, which one does the more risky surgeries, on and on. And you start comparing those to their length of stays, and you might find a comparison between them. Now we could do what's called a two-way repeated procedures. That's similar to the one repeated procedure, but includes the interaction effect. For instance, if an X-ray had an impact on the results for CABG procedures and length of stay. Let's say your X-rays the X-rays had to be read by a radiologist who wasn't in the hospital, and they had to be sent out. There was a delay in getting those X-rays back. That would add some length of stay. So when you compare performance of more than 2 groups, you compare observations of normal or ordinal values, which you talked about before. Now, what if the data that needs to be compared between the 2 groups is nominal or ordinal? That is, data for which a mean cannot be generated for a test like a t-test or an ANOVA. And then you do what's called the chi-square, which is useful in looking at that. And we're not going to talk about chi-square in this particular group because it's not used as often, but it's something else we can do. So chi-square is another technique. Now, we look at graphical methods for detecting changes in quality and performance improvements, and hypothesis testing and test of statistical significance are one method of determining if there's any change occurring in quality and performance with a group. And those statistical tests require large samples of data to be accurate. You can't do it with 2 different samples, so to speak. I say it differently. You can't do that with 2 samples that have very few people in them. So you're going to compare 3 patients from one place and 3 patients from another. You don't have enough data, enough of a sample to make that determination. Now, statistical tests tend to use aggregated data. They may cloud cited variations in the way processes are performed and outcomes. So if they're aggregated data, I call that homogenized data. The process of homogenization is really this. In milk, if you had raw milk and you set it in the refrigerator, the cream would come to the top, and the milk at the bottom would be mostly skimmed milk. So what they do is they have a process where they mix the cream with the milk. And in whole milk, it's all that cream. In 2%, it's 2% of the cream is mixed with the milk, and 1%, 1%. So it's homogenized. So if you took a sample from a raw milk, you'd see that the sample at the top was all cream, and the sample at the bottom was all skimmed milk. Where in homogenized milk, you take a sample anywhere in that, or the bottle of milk, or the jar of milk, or the carton of milk, and you see that they're the same. They have the same content of cream. And so sometimes that sort of clouds the statistical process because it makes you think that everything is wonderful and normal and average when maybe it isn't. So we tend to use graphical methods for detecting changes in quality and performance, and aggregate data and statistical analysis may focus more on average values than on individual performance, and that may not be as helpful as you think. So we use what are called control charts, which are pretty common visual approaches to evaluate performance and quality with associated rules to determine if the process is either in control or improving, or not in control or not improving. And this graphical analysis of performance data provides visual evidence of the variability inherent to the process. It really tells us that there's variability. And we'll look at different kinds of those. So variations in performance. The categories of variation in performance can be common or they can be special variations. Now, another name for common is random. That's the causes of variation that are inherent in the work performed. They affect everyone who performs the work, and it affects all the outcomes of a process. So in other words, what happens if you've had 10 people do a job, this common cause or variation would affect all of them. It's generally predictable and expected. Like, let's say you have to wait 10 minutes before you do the next step of your process. Everybody would have to do that 10 steps. So an example is the length of time it takes to triage a patient. The process there's some basic delays in the process. Now, special is assignable. That means the cause of variation that are external to system or work performed. They're due to special circumstances or special causes. An example is if you have a brand new triage nurse who would be not as fast as the others, or you have an improperly trained triage nurse who wouldn't be as competent or as fast as the others. So that would change that. So that would be a special cause, not the common cause that occurs to all the other triage nurses. Now we talk about statistical process control, SPC. It's a technique that QI teams use to improve or evaluate, predict, or control their processes. They do that through control charts. That's really a chronology, a chronological time series where we plot what our rates are, our indicators are, or metrics or other important variables over a period of time. And it includes an upper range and a lower threshold that says, okay, this is way out or this is way in, if you will. And we could use that using Microsoft Excel or a lot of other standalone software tools. It doesn't have to be too statistically sophisticated. Boy, that's a hard couple words to put together, isn't it? So you'd say that 3 times. So the idea is that we look at the process over a chronological time. So here we have the sample control chart, the sample, the mean, if you will, and there's the sample. We're going to say, okay, on day 1 this happened, day 2, and you go back and forth, and we can see that we have this upper level and we have this lower control level, upper control level, and we see this within control, and so this variation that we have is still within control. Now we do this a lot when we do controls on lab tests. So when we do a lab test on a human being or anybody, we do an upper control and a lower control that tells us that everything is the way it's supposed to be. And even though our samples may have variation inside this control, we know that our testing is still valid. It's still a righteous test, so to speak. Now, important series of control charts include features that are in control charts or data points. That's the little dots we just saw. These are the data points we see here, and they are associated with the process, the performance at that given time. We have the center line that's drawn at the mean value of the statistic, and then we have upper and lower control limits and the outer limits to the extent which is acceptable performance. And these are usually 2 standard deviations from the center line. And standard deviations are a result of a statistical analysis. It tells you. Let me put it this way: if you did a change, and the change, the pre and the post change was within 1 standard deviation, it would be that nothing changed. So if it's in 1 standard deviation, that means what you did didn't really change anything. It's still about the same. On the other hand, if you get out greater than 2 standard deviations, then there's a significant change. So let's look at this. So we have a sample control chart highlighting performance before and after change in the process. So there's our before and there's our after. So we're trying to lower this number. This probably length of stay. So before things were happening, this is what we saw. We made our change, and this is what we saw. We dropped down quite a bit after the change. Well, you can see that there was a change. You can see from here to here, there was a change because all the results here fall within the control, the upper and lower limits, lower controls, and so we see that even though after we made the change, we still have upper and lower control limits, and they still fall within. If they were going up and down and coming back up to this level, we would see that it was not. We did not create a change. So what you're seeing here is you're seeing that effect. And so this control chart, if you will, this run chart it's called sometimes, really tells you we made a change. We went from 9.2 down to 8.82, and that's a pretty significant change. We clearly changed the outcome. Now, the question, if this was over a great deal of time, if you will, and there was no variation based on certain parts of the month, for instance, like let's say this is the first part of the month, this is the last part of the month, and the first part of the month, if we looked at past information, we'd see that, okay, it's always like this to begin the month, and it always falls down here at the end of the month. So we'd have to compare this to a previous month, actually, to see from 1 to 30 some days to see if that really was a monthly variation. So if every month it dropped, we didn't make much of a change. On the other hand, if every month it was just like this all the way out and we made this change, we'd know that we'd done something. Now, data considerations for using statistical process control charts. When obtaining data for an SPC chart, it is recommended that there be a minimum of 20 to 30 consecutive subgroups or data points which are comprised of at least 100 consecutive observations. So you want to have a decent sample size is what it's saying. For instance, if sample SPC chart 9.2 was evaluated emergency department length of stay for patients admitted, it would be ideal to plot at least 100 admissions over a period of at least 20 days. That's what it's trying to say. So you want to be able to do that because it would be statistically significant. If you followed 3 admissions over 5 days, it wouldn't be quite as significant or quite as helpful. Now, the figure 4 we're going to see in the next slide outlines a set of rules that can be used to determine the stability of a process based on the plots of the chart. And these rules help quality teams to interpret the process patterns on the charts. They focus specifically on process variations. And then figure 9.5, we'll see after that, is a visual representation of the rules applied to 9.4. So let's look at 9.4. We see here's the rules. And so here we see we're looking at detecting stability in a process. So there's our upper control limit, there's our lower control limit, and this means that anything that's 1 point above the L or below the LCL would be here, 1 point above the UCL would be here. There are 2 to 3 points here, 4 to 5 points here. You see all this. Now let's go to the next slide, which kind of explains this. And what we see is we see that the sample of the SPC charts, we have 1 point outside the upper limit. We see that there. We see have runs of 8 points that are in these areas. We see that there's 6 consecutive points trending upwards, if you will, in these areas, and so forth. You see this through the process. Now, what this tells us is this, is that if we have 8 or more points in a row above or below the center line, that a significant change has occurred or a process may not be in control. One of those two things. So if we made a change and this happens, that tells us the change had effect, or that the process is way out of control. If we have 4 to 5 points between the first and second standard deviations, or between the minus first and second standard deviations, that tells us the same thing. Or if there's two of 3 points between the second standard deviation, that would be the positive second standard deviation, and that would be the upper control limit, or the minus second standard deviation, the lower control limit. And this is kind of more difficult to understand, but if it's up there, that would mean it's out of control, we made a change. At any 1 point above or below, above the UCL or below the LCL, that would tell us the same information, that we're either made a change or we're out of control. Now keep in mind that even if the value is within the upper control limit, the lower control limit, it may not be acceptable from the standpoint of this may not acceptable to patient or customer only. So if you lower the length of stay in the emergency room by hours, if you will, from 26 to 21, that may sound really statistically neat, but the patient may not think that's very important, that's very good. They might not see that as a great change. They may want to see that as a 2 hours instead of the 21 hours you went to. So that's important. That this means you had a change, but you may not have created enough change to that. Now there are different types of statistical control charts, and the selection of type of control chart really depends on several factors. The type of data being used, is it continuous versus discrete? The sample size availability, what is being plotted, percentages, counts, rates, or time between rare events. And you see a summary of the different types of SPC charts and a guide for selecting the best one which is in the available at healthcareanalyticsbook.com, and that's the website that's available that your book can give you access to. Now let's look at an overview. This is a way to look at how to pick common control charts and what they give you. So this is the discrete chart type. This is continuous. So discrete chart types are P charts, C charts, U charts, and T charts. A P chart gives you percentages, a C chart gives you counts, a U chart gives you rates, and a T chart gives you time between events. Now continuous, use an I chart, is sometimes called an X-MR, where MR is the moving range, and individually measures data points if you want that. The X bar is when you have subgroups of data at the same data point in time. So the X bar may be different. So these are the charts you would use based on what you're trying to gain or what kind of data you're trying to use. So let's talk about putting it together. Knowledge is a critical element in the development of analytics, and you need to understand who needs the information. Let me put this in kind of a metaphor, or not metaphor, but comparison. If I were to start talking in German, and you didn't speak German, this lecture would have no value whatsoever. If I start speaking to an audience in statistical techese, and they don't understand statistical techese, what happens is they don't understand what I said. I've made no impact. And so as the great drama people say, you have to know your audience. And so who needs the information? How can they best make use of it? So you have to provide a way, a means to give them that information. We'll talk about that in subsequent chapters. But you have to be able to give them information in usable forms. So you can just inundate them with garbage, of which they have all this garbage. They know they must make a change, but they don't know what the heck they're going to do. Or they don't have any idea what it says. You say, okay, the p-value of this was da-da-da-da, and the f-value was this. People are going to go, well, okay, what does that mean? Because most people either didn't take statistics or don't want to take statistics or try not to remember statistics because it's a bad dream. So SPC charts and statistical analysis help study performance of a process and its resulting quality. So QI professionals find value in these charts, obviously, and as well as statistical analysis. HCO senior leadership probably don't find value in these directly because they don't understand how they work. You have to give them something in a in a digestible form is the term we use. Put that all together. That's pretty important that you have that in mind. Now, nobody who needs what kind of information is important in developing effective analytics, because if you don't do that, you could be you have to know the audience, like I said before. And analytics provides deeper insight into performance, and instead of simply displaying a collection of graphs or charts or dashboards or reports, it can be made more analytical by embedding insights gained in targets. So you're going to give them some direction. You're going to lead them down to a place that says, okay, this is what we're doing. This is a sample dashboard. It includes embedded analytics. You see X-ray. This talks about performance dashboard. We look at X-ray order to patient pickup, pickup to X-ray start, X-ray duration, X-ray stop to patient return. It talks about all that process, and we start to see the steps in this process and how they're doing. We see our target, we see our baseline, and last month we see what happened, and now the current month. Now we're not at 10 yet, but we're a whole bunch below 33.2, which was the baseline last time. And last month we were at 22.5, so we even see significance there. So you're seeing that we're seeing some change. Now that's in our X-ray order to pickup. Here's the problem. Look at this. This is really kind of not changed. This is kind of not changed. And the X-ray stop the patient team, this has actually gotten worse. So what we're seeing, we can look at each one of those processes, and we can see each one of those steps, and we can see whether that improved or not. Now a change we made here may have made these processes worse. And so there's this what's called unintended outcomes. Now, the previous dashboard is a simple representation of an indicator, provides an overview of performance, and also includes embedded insights from both the statistical analysis and the SPC rules. Now, using statistical and non-statistical approaches to evaluate quality performance is complementary. You want them to work together, and so you want to develop an effective analytical tool which requires expertise, if you will, and a lot of effort as far as the analytical teams. And they have to understand the data content. They have to understand control charts, and an analytical professional has to be comfortable in embedding the basic statistical analysis, and what they're kind of leading the people where they need to go based on the data. So you want to be able to do that. So this is the completion of Chapter 9. Thank you very much.